Before we begin, I'd like to walk the audience through a few items. On your screen, you can see a Q&A pod. Please submit your questions for our presenter and Q&A moderator at any time. We will address them throughout today's presentation. At the conclusion of today's presentation, there will be 3 poll questions proceeding live Q&A. Today's webcast is being recorded, and we will send you a follow-up email with a URL to the recording once we verify the recording quality, as well as a link to the presentation deck. And again, welcome to today's webinar, Amazon Aurora Deep Dive. Our presenter is Lynn Ferrentine and Abdul Saint. Lynn is Amazon Web Services Senior Business Development Manager for databases. Before AWS, she worked for MYSQL, Oracle, and Sybase, and contributed to the development of open source software for the University of California, San Francisco. She has a master's degree in bioinformatics. Abdul is a principal product manager for Amazon RDS. Prior to this role, Abdul was a principal solutions architect, focusing on databases and enterprise applications workloads on AWS. Today with us, we also have Shandor Maurice, software development manager for relational databases. Shandor will engage with you and answer questions throughout today's presentations while our presenters present. Well, Lynn and Abdul, welcome, and now pass the floor to you.
Thank you, Bowen. Hi, everyone. Today in our session, we're going to take a look at Amazon Aurora, take a look under the hood, and see how we provide performance and availability. So if you're not familiar with Aurora, what we're trying to provide here is a MySQL compatible relational database with full ACID capabilities, but also that gives you the performance and availability of a commercial database while keeping that simplicity and effectiveness of open source. We've been working hard for a while. We went into production in July, and we've had great uptake. Aurora is the fastest growing AWS service right now. Here are some of the common use cases for Aurora, and as you can see, they're all across the board, from business applications, games, ad tech, IoT, e-commerce, web, mobile, and more. So let me show you some of the customers that are already using Aurora. You probably know Expedia. It's an online travel company which has 150 travel sites in 70 countries. They were an early Aurora user, and they needed a relational database for analytics and real-time BI for their travel marketplace data. They were on SQL Server, which was getting pretty expensive because the data volume was growing, and with an increasing data volume, also the performance wasn't doing well. So they tried a couple of things. They tried Cassandra, Solar Index. They were both a no-go. But when they used Aurora, they found a database that could give them scale and performance at an affordable cost. What they do in their application is 25,000 inserts per second with a peak of up to 70,000 inserts per second with a 30 millisecond average response time for writes and a 17 millisecond response time for reads, which are pretty impressive numbers. If you're in the West, you probably have heard of Pacific Gas and Electric. They're a large public utility company in Northern and Central California, and they have 16 million customers covering about 70,000 square miles. And they needed reliable scaling when they have high traffic surge events during loss of power or power surge, anything like that. So they found the 6-way replication in Aurora. We have 6 copies of your data across 3 availability zones, was a really good fit for them. Every piece of their data is replicated 6 ways, 3 AZs, and Aurora can have up to 15 read replicas. And those read replicas can be spun up very, very quickly since they all read off the same virtual storage device. And during an event, when you need to spin up replicas quickly, that worked really well for them. Another customer is ISCS, which provides policy management, claims, and billing for insurance. They were using Oracle and SQL Server for a long time. But what they saw in Aurora that they liked was the continuous backup into S3, which eliminates the need for a backup window. Also, they're offloading data from Aurora into Redshift, and that's working really well for them, and it's costing 70% less than SQL Server. And finally, let me tell you a little bit about Alfresco, which is an enterprise content management company. And they have about over 1,800 customers in almost 200 countries. They wanted to build a document repository in the cloud that would scale to 1 billion documents. With Aurora, they scaled to 1 billion documents with a throughput of 3 million per hour, which is 10 times faster than their current environment. Some of the customers that I've spoken about have done presentations at reInvent, for example, Expedia and Alfresco. You can see them on YouTube if you just look for reInvent 2015 Aurora. So let's talk a little bit about performance, and here's an updated slide on Aurora performance. In these benchmarks, we're doing over 100,000 writes per second and 500,000 reads per second on the MySQL Sysbench benchmark. And if you're not familiar with Sysbench, it's a common open source benchmarking tool. Started with MySQL, but I know now you can use it on other databases. And it can simulate read-only workloads, write workloads, mixed environments. So for the write workload, we used 4 client machines with 1,000 connections on each machine. And for the read workload, we used a single client machine with 1,600 connections. All machines were R38XLs in a VPC with enhanced networking to make sure that the throughput numbers weren't constrained by network bandwidth. So you can reproduce these results yourself if you like to. All you have to do is provision an instance. We have a white paper that shows some of the things you should be doing to get high performance. So, for example, you want to run multiple client machines. You should set enhanced networking on them. You need to tune your Linux settings to get the throughput you need. And on these benchmarks, we're running in the same AZ for client and servers. And you should be able to get similar numbers. Performance would obviously be lower as the instance types go down, as you would expect. So you see at the bottom of the slide, we have a link to that white paper. And you can also download, if you prefer, an Amazon machine image customized to make it easy to benchmark Aurora with Sysbench or TPCC that you can launch in your own account. So these are benchmarks, but the fact is that benchmarks don't really matter. I mean, if only you were able to see the values in your real-world application that were the same as in a benchmark from the various vendors, we wouldn't be looking at a new database. Why does it differ? There are a bunch of real-world distortions that happen that are different than what we talk about as database vendors. For example, requests contend with each other. And metadata rarely fits into the data dictionary cache, so you have to go out to disk. In the real world, data almost never fits in the buffer cache, so you have to go out to disk there too. And frankly, production databases need to run HA, and you aren't going to run something on a single node in the real world. So in the next few slides, we're going to show you how we're doing with respect to some of these criteria relative to MySQL 5.6. So here we're looking at user connection scaling, going up from 50 to 5,000 connections using Aurora. And as you expect, we're seeing increased throughput because Aurora is very much about trying to generate higher throughput. Here we're using the OLTP workload from Sysbench, which has a fair bit of contention baked into it with 250 tables. And if you look at RDS MySQL with 30,000 provisioned IOPS, which is about the biggest box we can put together, despite all the available capacity, it starts to decline quite early, which has to do with issues in lock sharding and how the threading model works inside MySQL. So in this case, our best numbers are about 8 times faster than MySQL 5.6. Let's look at table scaling when the tables no longer fit into cache. So as you go up from 10 tables to 10,000 tables, we definitely start seeing a little bit of a penalty in Aurora, going from a peak of 64,000 requests per second on a write-only workload with 1,000 connections, down to 54,000. But if you look at MySQL, you can see it's doing about 5 times worse as you go from 10 to 10,000 tables. And I think what's interesting to call out here is that this really has nothing to do with I/O. Whether you're looking at a local SSD, a RAM disk, or a fully provisioned PIOPS instance, the numbers are really about the same. This is really a testament to all the work done by the EBS team to ensure that they're operating at a pretty high throughput compared to local disk, but it also shows contention points that are going on in the database tier. And also let's take a look at data that doesn't fit in cache. So here we're looking, here we're scaling a database size up from 1 gigabyte, which can certainly fit in most any cache, to a terabyte. So Aurora is basically running about the same performance as long as we're fitting in cache. Then it drops down, as you would expect, once you can no longer fit in the cache by about 4 times. What's interesting if you look at MySQL is that it starts declining well ahead of that point while the data is still fully cached. And in this case, we're running 67 times faster, which is a crazy number, which made us decide to take a look at TPCC just to run something else. So we ran the Cloud Harmony TPCC-like benchmark, which is pretty much the same as the standard TPCC benchmark that the council runs. And here it's running, Aurora's running 136 times faster when it's not fitting in cache. And if you run read replicas, which people normally do, if you want HA or high throughput read queries, let's talk about the lag of read replicas between MySQL and Aurora. So MySQL read replicas really start to degrade, and the lag between the master and the slave goes up as you increase the updates per second through the system. In Aurora, we also use read replicas as failover targets. So going from 1,000 to 10,000 updates per second, we're relatively stable at about 5 milliseconds of replica lag, whereas in MySQL, we go from a few milliseconds all the way up to 300 seconds. So for the bulk of this talk, we really want to talk about how we achieve these results. The core of this comes down to improving your algorithms, sharding your locks, removing contention, and that's good, but basically anyone can do that. It's not architectural work. So now I'm going to hand over to Abdul, who's going to talk about some of the architectural work that we've done with Aurora. Abdul?
Thank you, Lynn, and welcome everyone, and thank you, Bowen. Just wanted to remind you, and we have a wonderful resource here, Shandor from our development team, and thank you, Shandor. He probably knows a lot more about all this than I do, but I get to talk about it because he actually was part of building this whole thing up. So feel free to send in your questions as you are listening to me. You can expect somebody is going to answer those questions, and some of those questions that we probably want to discuss more widely, we'll pick them up later on in the talk and continue with it. So continuing from where Lynn left off, the re-architecting of the database model for Aurora, we looked at how databases currently work. We looked at what is a great point to start off, and because of the adoption we have, and see how many customers run on AWS, and the nice features and available in MySQL, we thought that would be a great starting point for Aurora. So we took MySQL and rewrote a whole bunch of things, a great portion of MySQL, re-architected how that works, and then came Aurora from it. As Lynn mentioned, a lot of optimization actually went into the code base in improving the algorithms and sharding the logs and removing contention. But the bulk of the core work that makes Aurora what it is actually went into re-architecting the underlying infrastructure, the underlying design of how exactly the database works. So if you think about any conventional relational database, it has a monolithic structure where everything actually happens in that one box where the database runs. This includes the SQL processing, SQL optimization, transaction handling, caching, logging, everything that's related to storage for preparing the storage, and just the data blocks and the logs and bin logs and everything finally gets pushed out into the storage for getting stored. Whereas in Aurora, we took a look at this. We re-architected this based on a service-oriented architecture design and moved out a lot of different things into different parts of the entire database system. So probably like 25% of what MySQL does on the MySQL instance in Aurora is moved out into the storage system. We also took out the cache, which kind of like might sound a little crazy. I'll explain it a little bit more later. We took the caching layer out of the database system and moved into a different system where we can manage it better and it'll survive any database crashes. So just looking into what normally you do with optimizing your database systems, a lot of that actually has to do with the storage I/O. Because if you think about the database, eventually everything just goes down to the storage. And as the number of transactions grow and as the amount of data grow, it's all about I/O. The more you can optimize on the I/O, the better your database is going to perform. One other way of looking at is the more you can reduce I/O, your database is going to perform better. It's kind of like, just if you think about the freeway, you can go faster by either adding more lines or by reducing the traffic. There's only so many more lines you'll be able to add. So reducing the traffic gives you much better response and keeps the cost lower. And now if you add network attached storage to the picture, now it's not just the I/O that are important. The number of network packets that you are sending through also becomes important. If you use kind of like a high-end system like the higher-end EC2 instances with enhanced networking, we can actually do 1 to 2 million packets per second. But that is still a pretty constrained number. So if you really want to operate at high throughput, at high performance, one thing that you want to do is cut down the number of network packets that you are sending through the network and cut down the number of I/Os to to increase your performance and your throughput. Another thing to keep in mind is for better throughput, we want to avoid multiple system calls and context switches, because context switches are always very expensive. So if you look at this architecture, you see that the bottom block in green, the storage structure, a lot of our work actually went in there, and the layer between the top blue layer that you are seeing and the storage layer in minimizing the network traffic and the I/O. So you probably heard quite a bit about Aurora cluster. This is what we mean by the Aurora cluster, which is the Aurora primary instance and the distributed storage underneath it. The Aurora actually uses a 3-node storage, a 6-node storage cluster that's distributed across 3 different AZs. And when you are using Read Replicas on top of it, the Read Replicas make use of the same structure, so to minimize the lag, still using the same kind of storage mechanism that we are using for the primary. Let's take a look at how MySQL works to kind of like compare and contrast, so you can understand better how exactly Aurora works and which all points we have optimized to get better throughput and better performance. I chose to go with RDS for MySQL because RDS is basically a managed and engineered system where we already brought in a lot of optimization at the database level. We are doing automated replication to a different AZ, and at the storage level at EBS, we are doing mirroring. So a lot of things are already taken care of that you would otherwise manually do in a high-end production system. So just to go with comparing with RDS for MySQL, if you are actually setting up all this on your own in your own machines with replication and everything, it's still going to look very similar. So here we have RDS MySQL instance that is multi-AZ, means it's being replicated to a different AZ at the same time. You issue a write to your primary. The write goes down to the EBS in the primary instance, as you can see where you see number 1. The EBS automatically synchronously mirrors its own mirror, which is number 2. And then you go to the standby. So the write that you have done to the primary went to the EBS that's attached to the primary. It gets automatically replicated to the mirror of EBS. Then the same data actually goes to the standby. And we are actually doing this, under the wraps automatically without anything happening to the primary instance. So it goes to the standby. The same process happens on the other side, where the data goes to the EBS volume attached to the standby, and the EBS volume from the standby gets again replicated to its own mirror, which is handled by EBS. So you can see step numbers 1, 3, and 5 and are synchronous and sequential. What it means is any kind of network weather or network jitter is going to have a great effect on the performance of this whole operation. So the ACK back from this whole operation could be delayed 3 times or more if there is going to be any network delay, any network jitter, which happens many times for many different reasons. And one other thing to keep in mind is that MySQL does a lot of different types of write operations. So, when you are making one write, it is not one write that happens in 1, 2, 3, 4, and 5 steps here. So when you are doing one write, actually MySQL writes a log, MySQL writes bin log, MySQL writes data, and actually to avoid torn blocks, because your data is very, very critical, and especially when you are overwriting data in a block because it's a destructive operation, MySQL does 2 writes for the same data block. So basically your data is written twice now. So again, recapping, it's log, bin log, your data double write that actually goes through all these operations. So that's a good amount of data that you are shipping around to both the storage system as well as to the standby. And another thing to pay attention to is, unlike the logs that are being sent to the storage system, the data blocks are much bigger. They're a good deal bigger. They're normally about 40 times bigger. So now when you're actually doing 2 writes, we're talking about 80 times the size of log for your data blocks. That's a big deal. But like any solid database, MySQL is going to be doing a lot of batching under the covers to try to mitigate the overhead. We see that in all kinds of like performance testing that we do. So MySQL absorbs a lot of this kind of overhead and does a great job with taking care of all the overheads related to the 80 times the block size for the data. So what we did here is we took a 100 gig data set and we did a 30-minute write-only sysbench workload. And you can see the results we received from doing the sysbench workload. For what really matters from the sysbench is the response time and the transaction load in the primary, because for the standby, because it's just a replica, things happen automatically. What we have seen is within that 30 minutes, we can do 780,000 transactions, and we saw over 7.4 million IOs, which is pretty good if you consider the kind of like load that we throw at the database. Now let's look at how it performed when we did the same thing in Aurora. So what we did in Aurora was the exact same thing. We took the 100 gig load and did the sys workbench for 30 minutes on the same size of database instances. You remember the Aurora, the MySQL RDS instance had a 30,000 PIOPS EBS storage attached to it, which is the high-end storage that's available to RDS MySQL. Now let's look at how things happened in Aurora. So in Aurora, instead of moving data blocks, all that we are doing is shipping log records. So the storage that is underneath Aurora, that I talked about earlier, where we pushed out 20%, 25% of what happens in the database, it's a log structure storage. So all that we are sending to the storage is log records. We are not sending the data blocks. So you probably remember I mentioned previously in case of MySQL, where the data blocks are 40 times larger than the log records, which again, when you do it twice, it is 80 times. So what we are doing here is avoiding that much load for the I/O and avoiding that much network throughput that you would otherwise use. So here we are actually just seeing a whole bunch of log records. We boxcar them together to generate enough workloads that's worth shipping over, because we want to optimize how many packets we are sending over the network. And then on the other side, we have segmented the database volume across many small little segments. Actually, each segment is about 10 gigs. It's done that way to optimize one read and fault tolerance. Now the database volume, the storage is divided into multiple segments, multiple disks, and multiple storage volumes. So if we have to, we have to shuffle to make sure we have enough storage going into the storage node. That's why we wait till we get enough redo logs to boxcar them and send it over. So that operation is pretty complex, and as kind of like things that I'm mentioning, there's a lot of optimization that happens in just collecting them and shipping over. So once the logs go over to the other side, we persist them, and as soon as we persist them, we send an ACK back to the primary instance, acknowledging the database write operation is done, and the primary is ready to continue with whatever it was doing. So now you can see there in the storage area, we actually are replicating the write 6 times, unlike in the case of MySQL RDS, where you are actually writing to only one EBS volume, and then that EBS is taking care of writing into a mirror. So it's basically MySQL is doing only one write, whereas EBS is doing a second write. In the case of Aurora, we are doing 6 writes, so it's 6 times more log writes than MySQL, but it's 9 times less network traffic. So let's see what that does to the overall performance of the Aurora instance versus MySQL instance. You can see we did 27,378 transactions in the same 30 minutes as we compared to MySQL. Remember from the previous slide that for MySQL, we were able to do 780,000 transactions. So this is 35 times more transactions within the same period of time that we were doing the testing. And on the I/O side, we were able to do 950,000 I/Os for 1 million transactions. This is including 6-time amplification, because we are doing 6-time writes into the 6-way replicated storage. And you can see that is still 7.7 times less than what we were able to do with MySQL, because in MySQL, doing the same number of transactions or within the same amount of period was 7.4 million. So it is 7.7 times less transactions and 35 times more, 7.7 times less IOs, at the same time 35 times more transactions within the same amount of time. And that makes a huge difference. So you can see what we are doing, the kind of performance we are achieving in Aurora to a great extent is by reducing what we are doing at the database level. So this is kind of like similar to taking away a whole bunch of cars from the freeway. So we are reducing the I/O, and we are reducing the number of packets we are switching over the network, so we can actually do more with the same kind of resources. So what you see in this slide is actually where a lot of action happens. So once when you do a transaction in Aurora, the log, as I mentioned previously, gets boxcard together and sent over to the storage system. And once we receive the record in the memory queue in the storage system, what happens is, as soon as it comes in, it goes into an update queue, which is written on the disk. So once it is written onto the disk, because it is persisted, we immediately send out an ACK back to the primary database. So the primary database knows the transaction is complete, and it can continue with whatever it needs to do next. So it doesn't have to wait for everything to be done on the storage side. Now, remember, since we have a 6-way replicated storage, this needs to be done 6 times, and that 6 times actually happens in parallel. That writing into 6 different storage nodes happens synchronously, so that adds a little bit of lag to the whole system. But the good thing is we don't have to wait for all the 6 to be written to send the ACK back. The Aurora storage uses a quorum-based structure where if 4 out of the 6 are done writing, we send an ACK back to the primary saying the transaction is taken care of. Now, another very interesting thing we have done at the storage level is using a peer-to-peer gossip protocol to fill in holes. So not just the primary database system talks to the storage system. All the nodes in the storage system, all the 6 nodes that are distributed across 3 different AZs, they also talk to each other. They also talk to each other, sending in data if there is a hole in any one of them. So that way they're talking to each other, making sure everything is synchronous across all these 6 different nodes at the storage level. Once the log is persisted, later on there are asynchronous processes that go around that call us this, take the log and create database blocks out of it. So we update the database blocks, and as I mentioned previously, we have segmented the database storage into 10 gig pieces, so that is the maximum amount of data that goes into one segment, and each segment that actually gets that data as a database block also gets the corresponding log entry attached to it. So anytime if that data gets corrupted, it can be regenerated from the same log and be applied. So that again is a periodic validation that happens based on the CRC code on the blocks. So there are all these asynchronous processes that you see, which is, if you look at the slide, item number 6 and 7 and 8, these are asynchronous processes that happen which doesn't have any effect on the performance of the system. At step 2, we already sent back the ACK, so the system knows the data is persisted and it can continue working. And when it comes to database, performance is quite important, but probably reliability is more important. In no case you want to lose any piece of data. That is why we put so much emphasis on putting, so much such a wonderful architecture at the storage level. And you can see, the data is distributed across multiple segments within the node, and there are 6 nodes. There are two storage nodes per AZ. So we can pretty well tolerate any segments going bad, because there are processes that go periodically and check the segments and fix the data. We can tolerate the entire node going down because we have 2 nodes, so we actually have 6 nodes across 3 different AZs. We can also tolerate an entire AZ going down because we are using 3 AZs and we have 6 nodes across 3 AZs, and the quorum for the ACK back is 4. So if we have 2 AZs, we still have 4 nodes available. Now, in addition to this, we are also continuously backing up this data to S3. So just if you think about setting up a system on your own with such redundancy at the storage level, that's it takes a lot of effort and a lot of touch points and a lot of making sure that things work well. So here you can see at the step number 6. What happens is from each one of those blocks, the data gets continuously backed up to S3. And S3 is pretty much, the best persistence level you can get with 11 nines of durability. And we don't ACK back till actually the data goes to S3. So we ACK back as soon as the data comes into the storage layer, goes into the update queue, it gets written into S3 as a snapshot, as an incremental snapshot, and once that is done, we ACK back. So now your data that comes into the storage system, it is distributed across 6 nodes, across 3 availability zones, as well as it is stored in S3 for additional persistence. Now let's take a look at the the commits. So this is again another place where a lot of database have contention, and quite a bit of contention. The traditional approach is to maintain a buffer of log records to write out to the disk and issue a write when the buffer is full or time's out. So now the problem here is there is a first writer penalty or the first writer latency penalty, because the first writer writes into the buffer. The first writer would have to wait till the buffer fills up or it times out. In a very busy transaction system, probably the buffer fills out before it times out, but it still takes time, and the first writer receives that penalty. But when it comes to Aurora, we do it in a slightly different way. As soon as the first I/O request comes in, that fills the buffer. The writer picks it up, and as soon as it picks it up, it gets sent to the storage system and sends back the ACK. So now, though the transaction is not committed, the transaction that went into as part of there's a set of transactions before it's committed. It's now went into the storage system, and we acknowledge back, so the process can continue without the first writer penalty. And a similar thing applies to the thread pool also. We did a bunch of work on the thread pool. If you look at the standard MySQL thread pool, MySQL uses one thread per connection. It works for small transaction loads and small databases, but once you have a lot of connections, a lot of transactions, when you have a lot of transactions, you have a lot of connections to the database, it doesn't really scale very well. MySQL Enterprise Edition actually kind of like addresses this to some extent by using a thread group, but there's limitations on how well the thread groups also scales. Now, even in case of the thread group, you have to do a lot of experimentation with the thresholds to make sure you hit at the right point that gives you the best performance. Whereas in Aurora, we have a totally different thread pooling model or thread model. So what we did is we put ePoll in front of the thread queue. So the threads keeps looking at the ePoll to find out, what is the work that is available or work that needs to be picked up, and that gets pushed into a latch-free event queue. And the thread pools gets dynamically sized, so depending on the amount of work that is available, amount of transactions that are waiting, we can add more threads to the thread pool to pick up the transactions or release the thread pool so it can go do something else. And actually, a very good example for this is a set of transactions where the transactions are waiting on a log, so the threads are all used up, you have no threads left because they're all waiting on a log, and the log doesn't get released till a commit is made. So when a commit comes in, there are no logs available, there are no threads available, so it kind of like goes into this permanent lock mode because you don't have thread available to satisfy the commit, and then all the threads that are busy are actually waiting on the log. So in this case, in the case of Aurora, that's not going to happen because the threads are allocated dynamically. And we have tested this quite a bit, and it gracefully handles 5,000 plus concurrent connections per session. This was done on a R38 extra large. Lynn talked about all those numbers that we saw from testing using Sysbench, and in some of those tests we have generated quite a bit of connections. Some of them we have 1,600 connections, and we have done tests, and some of our partners and customers also have done tests with very large number of connections, and Aurora handles all those connections gracefully. Now, this is a very interesting contrast between Aurora and MySQL as well. You probably remember a while ago, databases had a streaming kind of capability where you would replicate to a standby instance by replicating the data as it is, as the data gets written into the rows and columns. And later, people figured out that's not a very efficient way of doing things because a lot of sync lag, a lot of drifting of the data, as well as the large amount of data that you need to send in. In previous slides, I mentioned the data block size is 40 times the log size. So later, many databases adopted this model of actually sending out SQL statements that gets applied to the standby. And that when that gets applied to the standby, it looks exactly the same as your master. And that's actually a very logical thing to do, and very nice way of replicating data. But a drawback of that model is when you are replicating data from master to the replica using this model, you are actually doing the same amount of work on the replica as you are doing on the master. So in the master, let's say your master is pretty write heavy. If it is 70% write and 30% read, and you are planning to use your read replica for read-only operation, so you are expecting you are going to get a lot of performance out of this because you are doing only read. But actually, your replica is not just doing only read. It needs to do all the writes as well, because whatever the master is doing, now your replica also has to do when the SQL transactions come through, or the SQL statements come through to the replica. It needs to apply all those SQL statements, basically doing the same processing on the replica as it is doing in the primary, causing the replica to do 70% of work for writing and making available only 30% of work for your read. Whereas in Aurora, the way we do it is completely different. The replica uses a shared storage as the primary is using. So you have 100% of the instance is available for your read load versus 30% available for your read load in case of MySQL. Now we keep applying continuous improvements to Aurora as we go. The great thing about going GA is we are getting a lot more feedback from our customers as they start using more and more of Aurora for a lot of varied workloads. We get a lot more feedback than we were able to find out during our initial testing and during our preview, and we continue to make those improvements based on what we hear from the customers. So these are some of the improvements we have made recently based on customer feedback. Some are about bin log, distributed transactions. We heard some really great feedback from customers about read-ahead cache. We were not doing very well on read-ahead cache because since Aurora is using its own storage system, we are not getting some of the advantages that Linux provides for IDS for MySQL. So those are things that customers pointed out, and we made a lot of improvements on those spaces based on what we heard from the customers. Now, when you look at the database, there are three things that are probably most important for a database, which is reliability, that I would classify as the most important thing, which we talked quite a bit about, and performance, that also we talked about, and then it is availability. So if the database is not up, the performance doesn't matter, right? So you want your databases up and available all the time. So when your transactions come through, your database is there to service it. So we talked a little bit about quorum system, which makes latency tolerant, and we can lose a node or a disk or an AZ and still run. We also have the GOSI protocol that I mentioned that fills in the holes in replication in case of network weather causing issues, if these nodes get out of sync. I also mentioned we continuously back up to S3 with no latency penalty. This also is kind of different from MySQL RDS for MySQL, or if you're running a database on EC2 where you are snapshotting from EBS to S3, compared to that, here there is no penalty for backing up to S3. It's something that continuously happens. I also mentioned about the 10 GB segments on the disk that the way we segment the data at the storage level. So the main reason is to keep the blast radius small. And also, if there are hotspots, we can kill one of these and move the segment somewhere else, because it's so small and the whole storage system is on a 10 gig network. Moving a 10 gig segment to another place is pretty easy and quick to do. Another key advantage of Aurora compared to the traditional databases is instant crash recovery. If you are a DBA, you know how painful it is when the database crashes. You bring it back up. It typically takes 5 minutes from the previous checkpoint to apply all the logs and bring the database back to the same place where it was before. Now, when it comes to Aurora, there is no such lag. Your recovery, your crash recovery is pretty much instantaneous, because for crash recovery we use the same methodology, the same system that I mentioned before for actual storage. So when an Aurora instance comes back up after a crash, in case if there is a crash, what we do is we take, depending on the request, when that data block needs to be read, we'll pick up the redo log that is attached to that data block and apply that redo log before sending the data back to you. In other words, when you bring back an Aurora instance, there is no need to wait for 5 minutes or 10 minutes for that recovery to the last checkpoint to happen. Your instance comes back immediately, and you can continue from where you left off. I briefly touched on this early on about moving out the buffer cache out of the DB process. It's kind of like a interesting architecture. So the advantage of that is the cache stays warm even after a restart. So if your instance crashes and it comes back, in the traditional system, when the instance crashes before the buffer cache, because the buffer cache is in the same system, when the instance comes back, your buffer is all gone, and it takes a while to fill up that buffer. And you cannot really, usually reload the entire thing to the buffer by doing a whole bunch of transactions quickly or a whole bunch of reads quickly, because that'll put a lot of effect on the system, and your system might go down again, which you don't want to happen. So normally you do the cache kind of like gets warmed up by trickle. It takes a while for your cache to warm up. Until your cache gets warmed up, the number of the performance of your database is not where you want it to be. Whereas in case of Aurora, because we moved out the cache from the DB process, if your database crashes, you don't lose the cache. Your cache stays warm, and when you come back, everything that was cached is still in the cache. Now you couple this with the instant recovery. What that means is immediate availability, and because the instance comes back immediately right after the cache, because it doesn't have to wait for the redo log to be applied, and your cache is ready to go. It's still warm. And with a standby, the failover also is much faster and much more predictable compared to RDS for MySQL. So if you look at that in the slide, if you look at that MySQL section, that's how the failover happens. Your database goes down for whatever reason, and we have in the control plane, we have processes that continuously are looking for any failure. So it takes a little while for failure detection, because you want to make sure the database actually went down, because the failover process takes a little while. So you don't want to initiate the failover process without making sure the database really went down. So the failure detection takes a little bit. And if you look at that Aurora diagram, the failure detection phase is still the same. We are working on improving it further, but right now, in case of both MySQL, RDS for MySQL, and Aurora, it takes about 15 to 20 minutes to do that failure detection. And then once the failure is detected, then we go through this phase of bringing up the other instance in case of RDS for MySQL, and then doing the recovery, because you have to bring all the redo logs to the phase of checkpoint, and then do the DNS propagation. So in case of Aurora, you can see in case of RDS for MySQL, that phase of recovery is quite long. It could be 5 minutes or more, depending on what you're trying to recover. Whereas in case of Aurora, the recovery is instantaneous, and then the time it takes is just for DNS propagation. And for DNS propagation, actually for Aurora, there is a better option available. If you are using MariaDB connector, MariaDB has a really interesting, MariaDB connector for Aurora has a really interesting way of fading you over, because the MariaDB connector goes against the system tables to find out what are the read replicas that are available, the IP addresses of read replicas available, and it'll automatically fail over the connections to that IP address without waiting for DNS propagation. So basically there is no DNS propagation time. So mostly the time that it takes is to just quickly fail over to the read replica node, and your application is ready to be up and running. So now, depending on the size of the instance that you're running, it could take 3 to 20 seconds for this whole thing to happen. And the failure detection takes 15 to 20 seconds. So together, we're talking about anywhere from 18 to 40 seconds for the complete failover. And because if you are using MariaDB driver, it could even be quicker because there's no DNS propagation needed. If you Google MariaDB Aurora, MariaDB driver for Aurora failover, you can see a very interesting blog that MariaDB posted last week. It has step-by-step instructions on everything that you need to do to make this happen. They also recently done some rework on it to improve on this whole process. Now, this is one of the very interesting features of Aurora that I like playing around quite a bit. In traditional systems, you have to physically crash your systems to try out things. You have to, if you have a standby, you want to see if you can actually fail over to the standby, the way everything is set up, how quickly it can fail over to the standby, how quickly the redo log gets applied. All this you have to actually do yourself by forcing it. Whereas in Aurora, we have a whole bunch of system calls that you can invoke to basically simulate the same thing, so that you can try things out by yourself. I think I took a little longer than I was originally planning to do. We are 3 minutes over, so unfortunately we don't have any time to go through the questions that I was supposed to address after the webinar. So hopefully they were all addressed by Lynn and Chandor while I was talking. Thank you very much.